go in and make a really good product. And
Yeah.
people who are working for many years in technology, they're sort of saying, well, patenting is okay, but we know we're the only people who can make that thing.
Yeah.
So if we patent it, it's probably not even going to help because nobody will be able to reproduce it anyway. So
Yeah. Between
the,
that, between that and defending your patent, it could
yeah,
take up
because
an awful lot of the time.
once you patent it, sort of by implication, people think, oh, this is a really valuable thing that we will try to repeat it. But if you'd never patented and just made a product, you would actually find nobody would find out about it.
Yeah,
Because
I read a thing about that saying it was trade secret was better than patent. And I
uh,
thought it was an interesting opinion, you know, like,
well, the interesting bit is that if you're talking about nuts and bolts, the things that you can see, that's easy. So it's easily copied and remanufactured somewhere else.
right, right.
Reverse engineering a formulation containing nanomaterials, not graphene in particular, but all sorts of nanomaterials, is virtually impossible
Sure.
because it's not only the fact that it contains certain materials, but sometimes the way you add them,
Right.
the way you functionalize them or heat treat them, even the sequence of these events may change the actual product.
Yeah, that's what they were saying about the concrete over in the
Mm.
UK, and that was where the recipe made a difference. You couldn't just mix it up any old way. It had to be in a particular order, which it made it work. So
Yes,
yeah.
and for that, people who develop this, they really should be respected because it takes a lot of
Mhm.
iterations, a lot of trial and error, a lot of initial disappointments, and having no results, and bosses jumping on you saying this concrete will never work and all
Right.
that. But you just have to carry on because at some point, one of those procedures would actually give you a good mixture.
Yeah, definitely. It's not like adding chocolate chips to cookies. You know, you're not just gonna.
I think even that may be quite.
That's true. Well, if you have an idea in mind of your perfect chocolate chip cookie, right? Is it's not too melty and you get a chip in every
Exactly.
bite. It's all the same chemistry in the kitchen, chemistry in the nanoscale.
Yeah.
So that's very true. So your new report that came out, you explained it to me so well when you wrote it to me because I understood that you were talking about the ISO standards for nanomaterials that are more in a spherical shape rather than graphene that
Yes.
comes in flakes, correct?
Well, it's one of those things that we always struggled. It's not new,
Hmm.
but most of the particle measurement tools like DLS or PTA, like particle tracking analysis, or other sort of optical scattering tools.
Okay.
You have a dispersion in the liquid, you shine a laser on it, and you get some information out of the measurement, what sort of concentration you have, what sort of particle size, shape, etc. So most of these techniques, they work for particles that are sort of spheroids. Um,
Okay.
very you have to intentionally make a particle as a sphere. So you can actually buy reference materials that are spherical, like polystyrene spheres. But
Okay.
most particles in real life, they are not spherical at all. So what happens is that when you measure something, the measurement technique sort of gives you an equivalent diameter or an equivalent spherical diameter of the particle. Even the particle is like in all sorts of
Sure.
sticking in all directions. And that measurement has to be sort of interpreted with a certain level of trust. In ISO, quite a few measurement techniques, they actually specify the aspect ratio of 2, which is the maximum. So the aspect ratio is calculated by the biggest to smallest ratio of sizes.
Okay.
So in this case, 2. Um, so for example, you can't. So it's basically an oval. So
Hmm.
anything bigger than that in one direction or flatter in that direction is no good for these techniques. Um, So for that reason, there are other techniques. For that reason, there were specific documents at ISO that were generated to actually look at graphene
Mm-hmm.
or other 2D materials. It seems that they share the same problems, and so we see very useful techniques such as SEM, scanning electron microscope, TEM, tunneling electron microscopy, of course. But then for graphene, you need to check whether it's graphene or not. So you have Raman.
Right.
And in many areas of the world, US in particular, people really like BET, which is the specific surface area measurement. One has to interpret it with a pinch of salt, because the pristine graphene that you would expect, a very high specific surface area, basically, it's the overall surface area divided by its volume. That surface area, when measured, is actually quite low, and it's surprising. But it's not surprising for physicists, because pristine graphene doesn't. So it's measured by adding gas on this surface, and then once then you add gas it, you measure the amount of gas, and you work out backwards what the surface area was. Problem is that the graphene, really good quality pristine graphene with no chemical bonds attached to it, it doesn't add, or the gas doesn't stick to it. So the measurement is not a full surface, it's only partial. So you get very low specific surface area for graphene samples that may be extremely high quality. While the bad ones that come from, for example, reduced graphene oxide, they're not bad, but they would have inherent dangling bonds and various other functional groups attached to them. So then the gas attaches very nicely, and we will get a really high specific surface area, while quality of the graphene is questionable. So again, courses, if you prefer the reduced graphene oxide for your application, that's great, because it may bind to some material. Pristine graphene is actually maybe a bit difficult to work with. Yeah. So this sort of thing, we found that requiring somebody to do the specific surface area measurement wasn't actually clever, because then you would rule out a lot of really good samples. But it's not because of graphene, it's because of the measurement methods that didn't really stick the gas on a very, very pristine surface. So
that makes sense. I get what you're saying, and I'm curious, is there anything that hasn't been invented that you would want them to do, like some sort of a combination or something to develop that would measure it better?
Oh wow. That's
maybe a tough question. I don't know.
Well, there is constantly a development of new methods, refinement of the old ones.
Sure.
Even the one that I just mentioned, the BP, it is refined as we speak. There's a technical committee, TC24SC4, that's working on this, and they're trying to use another gas in that. So that the old ones are being refined for the needs of today, and obviously new methods are being created, but they're not really created that quickly.
Sure.
So because it's, well, electron microscopy existed for so many years. It's only now that we come to use it for all these materials. So so there's still a lot to learn. I'm optimistic. There probably will be.
I think
pretty much. So there are laboratories. It's actually quite an interesting case to look at. Possibly all the laboratories that do this sort of work.
Yeah.
It's an important thing for building of the trust to also a reputable laboratory looking at your sample.
Yeah, so and I don't think we don't really talk about them very much. We're talking about all
No,
of
this is
the fancy things, and it's the stuff behind the scenes I think a lot of industry wants to know so that they know what to do and who to trust when someone's coming to them and saying, "Hey, we could really improve your product with graphene, and here's some ideas." And to try to help educate the industries, which are many. That's the thing. There's
well.
so many.
My experience is that the industry is rather clever, and it's I don't think we need to educate, but things are changing quite quickly, and it's
Yes.
more like keeping them informed.
Gotcha. Gotcha.
For example, things are changing. There's like new procedures that are coming out. We had some of the there was a structural characterization document that came out from the ISO that was led by NPL. They have
Hmm.
good guys working on this. So now it's an ISO standard. It's actually going into the European CEN approval as well. So it will become a European CEN. For those who are in the UK, UK is still part of the European CEN. We haven't really Brexited that. Um,
Okay.
but this is actually quite helpful. That means that there is a level playing field for everyone. And I'm hoping that the laboratories, they go a little bit behind, so it's maybe 1 or 2 years behind that. They have to take time to read it,
Hmm.
approve it internally, and then get qualified as certified laboratories for that procedure.
Okay.
Um,
Now, I noticed something from what you were saying when, especially when you mentioned countries, and so I'm very curious about this. When you work with ISO or any of the other organizations on standards, um, are there, is it the free world? Is it are we talking about globally having these standards for global use? Are there countries who just don't participate?
okay, well, I can talk you to till the evening about the ISO. The ISO is an organization where there is a certain number of countries that are participating.
Hmm.
All of them are P members, participating members. So they have a full vote. They have full rights to participate in every document, in every working group, and every study group, etc. And there are also observing members.
Okay.
The smaller countries. I can't remember which ones are. They sometimes shift from observing to fully participating members.
Okay.
About 39 participating members now, and about I think it's 18 or 16 observing members. So you can imagine that if you in the UN style, if you have a table and you have like all these representations with flags, this is what it's like when we have our plenary. Obviously, not everyone can make it to the meeting. Online meetings made it a little bit easier. So we have the smaller countries that got more energized that participate. And each country has a standards organization, national standards organization. So for example, for US, it's NIST.
Hmm.
Or for France, it's AFNOR. For UK, it's BSI, British Standards Institute. And so this is this national hub for all standards. So that organization actually has its own committees, national committees. And for example, for the UK, we have the weird name, the NTI1. It's one of the mirror committees that looks at all the activity for nanotechnology.
Okay.
So members of that, I'm a member as well. They are looking at all the standards. They're participating in meetings. They are assigned to certain documents or work items,
Hmm.
depending on their speciality. So, for example, I wouldn't know much about Raman, but I know a bit about the particle tracking analysis or SEM or TEM. So these are the things that you become a national expert by being appointed from the UK to these. And if you can, obviously you go to the meetings. We organize meetings, and meetings are rotated all over the world. So this autumn, ISO TC229 will meet in London, which is great. Not great for weather, but in November. But
Good location.
home because it was UK who actually created ISO TC229 originally created by a chap called Peter Hatto. So when I started actually participating as just an ordinary UK expert, he was chairing. So he's a legend.
Wow.
And so all these meetings, they're rotating all over the world, and we go to these meetings, and it's actually really useful to meet people face to face, because there's a lot of formal meetings as you have. You go through the agenda, you go through the comments, you go through some of the concerns that people may have with a certain document, you rewrite things. It's quite busy. A lot of discussions are also taking place in coffee breaks, where unofficially people say, well, actually, do you know what? I really still have a problem with this. And then they discuss, and then maybe because we schedule some meetings that are broken up with, through coffee breaks, then they come back and they have another angle to resolve the situation. So it's actually quite useful. We really suffered without having face-to-face meetings for the past 2 years.
That is hard, because it is those moments when you kind of take an aside and have that little chat, and you're not going to do that in a Zoom call, obviously. I mean, maybe you can in text to each other privately, but that's not the same. It's just not.
No, it's not the same.
Yeah.
It's not the same. And for me personally, when I lead quite a lot of discussions, I'm sort of involved in a lot of documents. For me, it's important to know what's happening. If not able to, because, for example, at the same time, we have like 5 different working groups in parallel.
Wow.
So I cannot be in 5 different places. So I sometimes shuttle between the discussions. And it's very important for me to know what's happening. So I'm standing at the coffee break, and people just come and quickly brief me on something, and they go, and I have another conversation for me to be informed. And I really value that. And face-to-face is the only way to do it. Well,
all right, we're getting to our
an ISO coffee shop on one of the plenaries. Well, it was sort of successful.
That's great. That's great. All right, we're getting down to our 2